Good morning, anatomy classes. Chapter 14, second part, as far as lecture goes. Kind of looking at this chapter in a long view. We'll probably have some form of assessment at the end of next week. Today will be the last day that I give you any type of assignments. I haven't decided if I'm going to make that due today or if I'll just make it due next week at some point. It'll probably be next week at some point. Chapter 14 is on respiration, the respiratory system, which is an obviously very important chapter. Breathing is one of those functions in the body that maybe is more familiar even to the person who's not that familiar with how their body works. Breathing, heart rate, those type of things. This also ties together the previous three chapters nicely. So understanding how this chapter works, understanding not how this chapter works, but the material from this chapter works, will be very beneficial for you moving forward, not only for the remainder of this year, but into next year in both of the classes that this lecture is for. The respiratory system's job, as you've summarized in your answers, I summarized in the last lecture, is to bring oxygen into the body for cellular respiration, and it's to remove carbon dioxide, which is a waste product of cellular respiration, or as a lot of you stated, cellular metabolism in your answers. The respiratory system's job, again, is relatively simple. Brings in oxygen, gets rid of carbon dioxide. Now, obviously, those are crucial processes. So when we look at the micro level, and a lot of you had really good answers, what happens, what is gas exchange? That's when oxygen by diffusion moves across the surface of the alveoli into the capillary bed surrounding the alveoli or the lungs, and then gets returned to the left side of the heart so it can be pumped to the body. Now, the respiration or the respiratory process, when we look at it in the other direction, gas exchange, carbon dioxide, is going to leave the bloodstream. It's coming from the right side of the heart. It's going to move into the alveoli. So it moves across that barrier of the lung into the alveoli, and then you exhale it every time you breathe out. That's what gas exchange is. You're exchanging carbon dioxide for oxygen. That's why the process is called gas exchange. Now, when we look at it at a larger scale, we look at it at the level of the lungs, not just the tiny alveoli, which I told you there's millions of those per lung. We look at some concepts here to help us understand how the lungs work. Tidal volume is the average amount of air that is going to enter and exit the lungs with a normal breath. So as I'm sitting here talking to you, I'm going to be breathing, obviously, while I'm doing it. That's the normal amount of air, the normal volume of air that's going to enter my lungs and exit my lungs every time I take a single breath. Now, if I was running around the table here while I was doing it, that would increase, obviously, because you're going to need more oxygen. You need more oxygen because your muscles are active and they're requiring more energy. Again, that tied to cellular respiration. That's why you breathe faster when you exercise. You need more oxygen and you need to get rid of the carbon dioxide. You need more energy, so oxygen has to come in to break down the glucose. Now, tidal volume, normal tidal volume for a person of average health is about 500 milliliters, which is about the size of, I don't know exactly how many milliliters are in one of those water bottles that you carry around, but it's a small amount, right? 500 milliliters, cubic milliliters, not a large amount. That's called the tidal volume. Tide being like the water coming in and out. That's why it's named that. The vital capacity is the amount of air that I can take in a single large breath. So if I sit here and I decide I'm going to take in the biggest breath that my lungs can hold, if I do this, and then let it out, that's the vital capacity. That's the max amount of air that I can bring into my lungs with a single breath. For a healthy person, that's about 4 times the amount of the tidal volume. It's about 2,000 milliliters, which is a big Erlenmeyer flask, one of those flasks that I have in the front of the classroom. So 4 times the amount of the normal tidal volume. The residual volume is the amount of air that remains in the lungs after each time you exhale. Now that sounds kind of strange. Why can't I get rid of all of it? So, I have all this air that's just been exhausted of its oxygen supply. It's full of carbon dioxide. I want to get rid of all that air, but you can't, and you won't. What's left behind in the lungs is called the residual volume, like the word residue, something that's left over, right? That amount of air is necessary. The lungs have to remain at least somewhat inflated, because if they don't, they will collapse under the pressure of the air pressure on the outside of your body and your thoracic cavity as well. So they have to remain partially inflated. That's why a collapsed lung is so dangerous. That's when it loses its attachment to the wall of the thoracic cavity and it deflates. And you can't inflate it again, because for whatever reason there's air inside the thoracic cavity. It could be because of an injury, a broken rib. All those things can cause a collapsed lung. So this residual volume is the amount of air that remains in the lungs after you've exhaled. So even if I sit here and blow out as much air as I possibly can, there's still going to be some air left in the lungs, and it's just a pressure gradient type of deal. That's how it works. So that residual volume is important. Now, that's not the same amount of air or the same volume of air that's been in there since the time you've been born. There's not this stale, nasty pocket of air that's stuck in your lungs. Every time you take a breath in, it'll mix with that residual volume, and then some of that will come out. So it's constantly being recycled, but a little bit has to remain in the lungs to keep them inflated, even as you're exhaling or expiring. Now, when we look at what's called ventilation, you can see there's a line in your notes here. Ventilation is two phases. It's inspiration and expiration, and all that is breathing in and breathing out. So when I inspire, right, that is taking a breath in like that, right? That's inspiration. Expiration is taking a breath out or letting a breath out. Exhaling. Now, I will ask you a question about this, and I'll tell you about it right now, but I don't have, obviously, any notes written on the board behind me because it would require too many and too much time for a short video like this. So you need to look at this in the notes as much as possible. How do you distinguish these two phases besides the fact that this is breathing in and this is breathing out? Inspiration requires energy, right? In order to inspire, to take air in, your body has to do some muscular contractions, the skeleton has to expand, you have to create space for this air that comes in. So what happens during inspiration is that I take in a breath like this. My rib cage, the muscles in between my rib cage, if you remember the name for those, that's the intercostals, right? They expand my rib cage. My diaphragm is going to contract. That's the muscle beneath my lungs. When it contracts, it drops. And when it does that, it decreases the pressure inside of my thoracic cavity. Decreases the pressure. Now you have to think about what that means a little bit. If I have less pressure on the inside of my thoracic cavity, that means that the pressure on the outside is greater. That means that air is going to flow in, because the pressure, if it's greater on the outside, is going to push air into my lungs. So what you're doing when you're taking a deep breath, expanding your chest cavity, is decreasing the pressure on the inside, so that allows air to flow in. Now, consequently, if you need to, obviously when we need to let the air out or to expire, or exhale, what you do is you just relax everything. So you just kind of relax, your rib cage goes back to its normal position, the diaphragm rises back up again as it relaxes, because as I said, when it contracts, it drops. And that is going to increase the pressure on the inside of your thoracic cavity, which is the same effect of you grabbing a balloon and squeezing it, because you're increasing the pressure around the lungs, and it's going to force the air out. That does not require any energy from the body. All you're doing is letting your muscles relax and go back to their normal positions, your skeleton, your rib cage go back to the normal position. So expiration does not require any energy, where inspiration does. It's a good point to look at when you're trying to differentiate these two topics. Have a good day. I will be in touch. I'll have some other notes written for you, just kind of guidelines and stuff where we're going with the chapter, and obviously I'll have a weekly guideline for next week. We start on Tuesday next week. Have a great day. Bye.